Okay, and welcome back to our Flownet video, like a second video on Flownets, basically, where I just show you a couple of calculations, couple of example calculations. So the first one here, remember from last time how we drew the Flownet. Now that we have a Flownet, we can calculate things, and one thing we can calculate is the maximum exit gradient. So here's the slide, basically, where you can see, so this is the same Flownet as we did last time. Remember, this was 20 feet of head difference between the reservoir and the river. And you can see here, so the maximum exit gradient is essentially the gradient here on this cell that is at the toe of the structure. Now, this is really important because that's where erosion might happen, right? So imagine if you have a ton of velocity, exit velocity, or a ton of flow coming up here, right? Now we're starting to erode at the toe of that structure, and if you erode enough, right, the whole thing is going to become unstable and fail. So obviously we don't want that. So this is a quick, simple calculations that we can do to ensure that our design, right, is good. So in our case here, we're saying delta L min is 4 feet. Now what is that? Let me show here, maybe blow this up a little. Okay, so what we call delta L min is the size of this cell. Remember, we can draw little circles in those things. This is supposed to be a square, right? So essentially all the dimensions should be about the same. So 4 feet is the size of this cell. Now again, remember, in a real life situation where you have a flow net that you've drawn, right, you can literally use a ruler and you have a scale to this thing. Actually, I told you, well, this would be 20 feet if it's at scale. I think on the top, at the top of the lecture, I said this would be 60 feet. The point is there's a scale to that drawing, and you can just measure with a ruler, you know, what delta L min is. Here it's just given to you. Now the maximum gradient, right, is just, again, by definition of hydraulic gradients, change of head over change of distance, right? So the change of head is the head drop per square, okay? So the head drop per square is the total head drop divided by the number of squares, right? So remember from last time we had 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 squares, which means we're dropping 20 foot, you know, across this whole structure, across 8 squares. So each square is going to drop, right? The head drop per square is going to be 20 divided by 8. So this is what we have here. And this is it, right? Really, this is, okay, the head drop per square times the smallest square is the max gradient you're going to have. And finally, you know, you can just calculate that as 0.625, so 62% is the hydraulic gradient, the maximum hydraulic gradient. Now, as a design, you know, problem, typically we're saying if the gradient is less than 1, we shouldn't have too much erosion problem. You know, that's just a design criteria, so this would be a good design. But this is an example of calculation that people used to do with Flownet, excuse me. Okay, another thing that's very, you know, that people use Flownets for is calculate the pressure at a point. Again, the pressure at a point is very important because if you have, you know, too much pressure somewhere, you start erosion or you start liquefaction of soil. So these are, you know, very geotechnical, basically, problems that, you know, most civil engineers would have seen in geotech engineering, for example. But as an example calculations, right, what is the pressure at point A, for example? So again, you can take any point in the domain and you can calculate, with the Flownet, you can calculate the pressure though. So it's quite powerful. So let's do it. So at point A, the total head here at the top, and let me maybe take a blue color just to change. So here at the top is the definition of head, right? Total head, again, for subsurface groundwater flows, we usually ignore velocity, right, because it's so small. So the total head is the pressure head plus the elevation head. And the pressure head, again, is the pressure divided by the specific weight plus the elevation. If you don't remember those definitions, please go back to our, you know, definition of head that's in this course. Now we can rearrange this to find the pressure at point A, right? The pressure at point A here is just rearranging that equation, gamma times, so gamma is the specific weight, gamma times the total head minus the elevation. Okay, well, what is the total head at point A? Let's calculate it. Well, it's just the head at the boundary. So here, this is the boundary, right? The total head at the boundary minus the head losses. So we're crossing, again, remember we have head drops per square in that FlowNet. So we're dropping head, at each square, 1, 2, 3. So here we have 3 squares that we're dropping to A. Again, we chose A on a line, but of course, if A is, somewhere in the middle, you can just say that blue point here, B, at B would be, 4.5, 4, and then 0.5, right? So you can calculate it anyway, it doesn't matter. Okay, so for A, we have 3 drops, so head loss per drop times the number of drops, and that's really it. So if we do this calculation, down here is the calculation, we have the head at A is 60 feet, so again, remember the boundary head here, right, that's 60 feet because I gave that before, but this is 35 plus 5, 35 plus 5 feet, and then this is the 20 foot of pressure head. So the total head at the boundary is 40 plus 20, 60 feet. Okay, so that's just given to you. I guess I removed the slide so you don't have the datum, but the datum is really important. So the elevation head here is 35 feet plus 5 feet because the structure is 5 feet inside the aquifer or inside the soil. Okay, so that's just given to you. All right, so 60 feet minus, so the head drop the head loss per drop, so we calculated that last time, right? 20 over 8 times the number of squares, 3. And if you calculate all that, you end up with the total head at A is 52.5 feet, okay? Now finally, we can calculate the pressure at A, and this is just given by gamma, so 62.4 pounds per square foot, times 52.5, which we just calculated, right? This is HA right here, minus the elevation at A, and again, remember this is 35, I just explained that, right? 35 feet from the datum, so minus 35. And if you put it all together, that gives you 1092 pound per square foot. So this is the pressure at point A. Okay, now why do we care? Again, the pressure, it's intuitive that it's pretty important, but one thing that's kind of an obvious use of those pressures is that you can do this at all those different points here, right? You can calculate the pressure at all those points, and from those pressures, you can calculate actually the uplift force. So let's see how that would work. So what is the uplift force on the base of that structure? Now, why do we want to know that? Well, it's pretty obvious here that the uplift force, if you remember from, hydraulics or any, fluid mechanics class that you might have taken, you can see intuitively that looks like this, right? So forces on the plane. So here the maximum force or the maximum pressure up is going to be, on the left of the structure because that's where your, 20 foot here. That's where the maximum head is, and then, it's going to decrease going to the right. And again, we just did the calculation at this point, but you can do it at any of those points, right? Once you have all those pressures, basically the force, if you remember, right, force is just the pressure times an area, is going to be just the sum of the pressure at all those points times the incremental area. And so again, if you calculate the pressure at each of those points and then you sum them all up, basically you get the total force up. And of course, the total force up is important because if the force upwards is more than the weight downwards, right, then the whole structure is going to lift and be, and fail again. So we don't want that. So an easy way to, account for those forces up is obviously to build a structure that is heavy enough that it won't fail. Okay, and finally, the last slide I wanted to show you is examples of cut-off walls. And again, if you've taken, geotech or other classes in civil, you've probably seen that. Otherwise, maybe not. But one of the problems that I've described, right, is the outflow right at the toe. That's where the maximum pressure and flow out is going to be in these kinds of structure. One way you can reduce this amount of flow out is to put cut-off walls. And a cut-off wall, here you can see an example. This is a cut-off wall. Here is a cut-off wall, right? And here is a cut-off wall. So these are 3 examples where you have a cutoff wall. What they do essentially, and you can see it maybe best on this example here in the middle, you know, the top one is just a dam like we've seen, and you can see all the equipotentials there. The bottom one has a cutoff wall, and you can see that now our equipotentials, right, are distributed differently. Now if we draw a flow line, let's say starting here, and it crosses perpendicular, now it has to go all the way down here and then back up here, let's say here. Whereas here before it was like this, right? So you can see for the same amount of flow, assuming there's the same amount of flow, right? Everything is the same. The only difference is the length of that flow line is now a lot longer, right? So again, if you have the same flow, but a much longer flow line, it's kind of logical that it goes a lot slower, right? So the flow is slower, meaning those pressures out here are going to be much less reduced with that cutoff wall. And that's why we use cutoff walls, right? We put a cutoff wall so that those flow paths are much longer, and now we don't have such issues with the pressure at the toe of our structure, erosion, and potential failures. So just by adding like a cutoff wall inside, you know, the ground, now we're really helping our structure to be a lot more stable. At the bottom here is, you know, as a reminder, you can do this in Excel real quick, right? So it's not, you know, as fancy as other, you know, software that are more, you know, that are advanced and made for engineering, like the top one here, the SIP2D software is made by the Army Corps, and that's a classic where you can do like FlowNets, you know, really eloquently. You can see that grid structure is pretty evolved, and you can grid refine around the wall, etc. So it's a much more, you know, advanced tool. But with our little, you know, Excel model like we've done in class, we can already, you know, put a cutoff wall here, and you can see that you do see the same patterns, at least, you know, if it's not perfect, you see the same pattern as you see with professional software. So this is really, you know, how it works. So you can do it by hand, you can draw a FlowNet and solve all those things, or of course, you know, nowadays you would use a computer software basically to input your domain boundaries and then find a solution for your FlowNet. Okay, I hope that was useful, and I'll see you in another video. Thank you.